In this demo, we will be demonstrating use of ClusterMol, which is a framework for clustering molecular dynamics, or MD trajectories. An MD trajectory is a simulation of the movement of a molecular system which outputs a set of frames that store the positions of each atom in the system at each time step. As upwards of 50,000 frames may be produced, clustering algorithms can be used to group the frames into sets of similar frames which can be manually analyzed to further understand the physical behavior of the system.
Initially, we give an overview of some of the testing and validation functions within the framework. Shown here is hierarchical clustering with Ward's linkage criteria formed on well-defined partitions of data. Additional testing datasets such as noise or random data, varied blobs, and UCI datasets such as iris, wine, digits, and breast cancer are available within the framework. Here we can see the resulting statistics from the clustering, including cluster counts and CVIs. Below we see a dendrogram from the resulting hierarchical clustering, and on the right we can see the correct clusters produced.
Now we will be illustrating the usage of HDBScan with UMAP preprocessing. For now, we're just focusing on the second section here. I've already started the clustering job to save some time, and now I'll just give a brief overview of what we're using. HDBScan is a clustering algorithm that uses a density-based hierarchy to cluster stable regions of high density and considers data that is too sparse as noise. UMAP is a dimensionality reduction technique that tries to estimate the topology of the given data and project it onto a lower dimensional space. The digits dataset that we'll be clustering contains 1,797 8x8 images of digits from 0 to 9. Therefore, it has 64 dimensions or features and 10 classes. Along with the plots generated by UMAP, we will also be looking at the silhouette score as the clustering metric, which ranges from values -1 and 1. A higher value suggests better clustering. Here's the output generated by the clustering job. On the left, we find the actual classes of the digits dataset, and the right shows the output attained by clustering using HDBScan with UMAP preprocessing. We can see that all 10 classes were found nicely, but some points were considered as noise, as indicated by the -1 label. This is confirmed in the result log, but the silhouette score is quite high, which indicates a good result.
We will now run the IMWK-means algorithm on an MD trajectory. The trajectory we are using is MEN-Y and has been downsampled to about 4,000 frames from 40,000 frames. The clustering job is being run with the parameters at the top of the screen. The save clusters parameter tells it to save up to 5 of the largest clusters, and the selection parameter is the atom selection statement, which causes atoms that are not part of the core structure of the molecule to be ignored during the clustering job. IMWK-means is a k-means variant, which is deterministic as it intelligently picks initial centroids. It also does not require a user-specified cluster count, as it begins by overestimating the required number of clusters. This algorithm takes between 5 to 10 minutes to run on this dataset, so this has been sped up. Here are the 2 clusters produced by IMWK-means. In each cluster, every second frame is superimposed and rendered simultaneously. Note that we are only rendering parts of the molecule that were clustered on. IMWK-means is particularly useful for identifying subtle differences, and that is what it has done here. The second cluster is relatively straight, while the first has a more pronounced curve. For the same molecule, HDBScan produced only one relevant cluster containing nearly 90% of frames. That cluster is visualized here. You can see that IMWK-means has separated that single cluster into 2 by identifying a subtle difference.
Here we show an example of the quality threshold algorithm, which aims to generate high-quality clusters by iteratively adding observations to a seed cluster while not exceeding the predefined cluster diameter or threshold. The threshold or cluster diameter was set at 3.5 for the MEN-W trajectory. In addition, we only saved significant clusters, so those that were greater than 100 frames in size. Above that, the 10 largest clusters were also exported as PDB files for further analysis. Cluster analysis information is also available, including the CVIs and cluster counts. Finally, we use VMD to visually inspect some of the clusters produced.